Hello, everyone. Today we're going to continue to study the chapter one. And today we're going to talk about the integral calculus. It includes three types of calculus or integral, which is line integral, surface integral, and volume integral. So before we start today's class, I'll recommend you to do some research or review of your previous calculus about the line integral and surface integral. So I provide two YouTube videos here. These two videos provided a lot of pictures, examples, videos, or movies to show you how to do the line integral and surface integral. The thing is, today in our class, we will um, do the line integral, surface integral directly from a vector function. So the calculations are based on the vector function. However, previously in your calculus, I believe you have learned more basic line integral and surface integral, which are based on not vector functions, but scalar functions. So in order to learn the line integral and the surface integral based on the vector functions, I recommend you to first review these two videos, and then you get some basic knowledge back. I suppose you might forget something. So just review these two videos. That's very helpful. And then let's continue to learn line integral and surface integral um, in the function of vectors. Okay, now I suppose you have finished reviewing all the videos shown here, and we will start from here. And I suppose you have the basic knowledge of line integral and surface integral of basic functions, normal functions, or scalar functions. And here we're going to learn line, surface, and volume integrals. Especially for line and surface integrals, we will use it a lot. And in many cases in this course, the line integral, surface integrals, they are based on the vector function. Okay, so here we'll introduce the concept and we'll give you some examples of calculating line integral, surface integral based on vector functions. In this course, we will have different kinds of integrals, which are line or path integrals, surface integrals, and volume integrals. So here, let's start from the basic integral, which is line integrals. So a line integral could be written in this form. So an integral from A to B, let's see, an integral from A to B for a function v. Um, please see this function is both function. It's a vector function, actually. So at any position x, y, z, it has three components, vx, vy, and vz. So it's a vector. It's not a scalar function. In the past, you have learned a line integral based on scalar function, I believe, in your calculus. You must have learned that. If you're not familiar with that, go back to your calculus or do a quick review from those two videos. Otherwise, in this case, v is not a scalar. V has three components, vx, vy, vz. Let's keep it in mind. It's a vector function. It's more complicated than what you have learned before. And then you have a dl here. Do you remember what is dl? dl is dr, actually. The infinitesimal position change or displacement. So if we show it in this figure, that's the integral. So first, from A to B, you have a path. This is a path shown here. So you want to do an integral along this path. So if you chop the path into small pieces or infinitesimal segments, you will see this is dl, dl, and dl. So it has a lot of dl's, which are shown in arrows here. Notice that your function now is a vector. So your v, for example, at the point A, it might be, let's say this is your v. It might be pointing in some direction. So v dot dl will be the dot product of two vectors. The first vector, of course, is your v or your function, and it's a vector function, and then dot product your dl. And at different points, you may have different v with different directions. So for example, at this position, you need to use v dot product dl. So you do v dot product dl in this path, and then you can calculate the integral. And also keep in mind that from A to B, you may have infinity numbers of different passes. For example, you can have another pass. I'll draw it in a dashed line. You can have another pass. Let's say this is pass 1. The dashed line I have drawn here is pass 2. So you may have pass 1, pass 2. You may have many different passes for integral from A to B. So when you choose a different path of integral from A to B, your result could be quite different. But sometimes for some functions, it might be the same. So the line integral for some functions, it might be independent from your path. It only depends on your starting and finish points. So in that case, we call that function conservative. Conservative function means, okay, let's read it again. If the value of a line integral depends on the path taken from A to B, that's normal, that's ordinary. However, in some special cases, the vector function, for some vector functions, the line integral is independent from path, and it's only depending on the A and B, starting and ending points. Then it will be our business in due course to characterize the special case of vectors. And such kind of function is called conservative. Okay. So a line integral could be written in this form, but in some cases, if the path in question forms a closed loop, or B equals to A, or the ending point is your starting point, then we put a circle on the integral sign, which is shown here. If we go back to this case, let's say if you have starting point, maybe let's draw another picture. Now, X, Y, and Z. If you have starting point A and ending point B, then you may have an integral like that. However, if you have starting point A, and then after a pass, you come back to A, let's say in this way. Or I can change to another color, which make it clearer. Let's see. Let's see in the red pass, you start from A and end at A again. So that's a closed pass. In this case, you use a circle on the integral side. Okay, so that's some concept of integral. Now let's do one example here for line integral. But I suppose you have reviewed the knowledge of line integral for the scalar functions. Then you can quickly understand the line integral for a vector function. So here is an example of vector function. So the vector function is v equals to this function. It's a two-dimensional vector function. In most of the case, you may need to calculate some three-dimensional vector functions for their either line integral or surface integral, etc. But it's similar. So if you can do a two-dimensional calculation, we suppose you're going to be able to do the calculation of three-dimensional cases. So now let's see, we have vector function in this way. So it has x component here and a y component here. That's why it's called a vector function. And from the point A to the point B, so point A is 1, 1, 0, point B is 2, 2, 0. So along the path 1 and 2, which is shown here. So for path 1, it first go to the right and then go up. For path 2, it goes directly from A to B in the upright direction. So along those two passes, what is a closed path integral of V for the loop that goes from A to B along 1 and returns along 2? Okay. So first, let's do the integral of, actually you can decompose the entire integral into 3 parts. First from A to, let's say this is C. From A to C, and then from C to B, and then from B to A. Okay, let's see the first integral. It's from A to C, and then we calculate C to B. That's the integral of path 1. Path 1 equals to ACB. Path 2 equals to AB. Okay, now let's first calculate path 1 and the segment 1, which is shown here, I. For the path I, what we can do is first dl, of course, or dr equals to dx in x direction plus dy in y direction plus dz in z direction. So this is easily understandable. And path 1 consists of 2 parts, which is I and double I. Let's first do I. For I, let's say dl. So dl is dx in x direction plus dy plus dz in y and z direction. But in I, in the path I, the y equals to 1. Y is a constant. So dy equals to 0. Z, of course, is also a constant. It's 0. So dz is 0. So dy, dz is 0. Then dl equals to dx in x direction because it doesn't have y and z direction. They're 0. Okay, so now dl is down. Now, we also know y in this I pass, the value of y is 1, then let's calculate v dot dl. So v is shown here. It's a vector. If we use v dot dl, then it has x components. Here it has x and y components, but dl doesn't have any y components. So the dot product will not result in any y component. It should be 0 in y. So it only has components in x direction. So dx times y squared, it becomes y squared dx. So this is v dot dl. So the integral of v dot dl equals to, let's say, integral of dx, because it's just dx. Let's see. Sorry, it actually v dot dl equals to y squared dx. So it should be y squared dx here. Okay, it's missed one step. It's a y squared dx. However, y equals to 1. So it's a 1 dx squared. So it should be, the y squared could be ignored because it's just 1. So it's integral from 1 to 2 of dx. So this value is 1. So the integral from a to c is 1. Now let's see from c to b, or double I. In this case, let's see, x equals to 2. It's a constant. So dx equals to 0. dz is 0, of course. And y, in y direction, let's see, x equals 2. So we only have the y as a variable. So the y is a variable, x is constant. Now dl becomes dy, because dl equals to dxx, dy, y, dz. So dx is 0, dz is 0. You only have dy in y direction here. So it's dy in y direction here. And as we said, x equals to 2. So v dot dl equals to, let's go back to here. In y direction, it's 2x y plus 1. So 2x y plus 1 times dl, which is dy. So dy here. Then let's see. Your x equals to 2. So dl becomes 4 y plus 1 dy. So the integral becomes 4y plus 1 dy. So this equals to d. So y becomes 1/2 y squared plus, this is 1. So here it should be y. So if you're not familiar with y plus 1 times dy equals to d 1/2 y squared plus 1. If you're not familiar with this step, you need to go back to learn some basic integral knowledge. So this is a commonly used transform. And then you would do a calculation of this function from 1 to 2. And then after calculation, you will get, it is 10. Okay, so this is for double I. So for I, you get the integral equals to 1. For double I, you get 10. So from A, C, B, from A to B in the path of 1, you will get it. You will get the integral to be 11. Now let's see past 2. If we calculate past 2 from a to b, so what we can do is in the past 2, x equal to y, so dx equal to dy, because if you see this past, x equal to y. Dz is 0, so dl equals to d. So now dl, it's a function of, it depends on x and y, both of x and y. It's independent from z. Z is 0, so dz is 0. So now you have dx and dy terms. So v dot dl becomes, now you have x term, y term, and use this dot product dl, you will get this form. And then notice that because x equals to y, so dx equals to dy. You can substitute dy here to be dx. That's the trick. So now in the v dot dl function, you have only dx. There's no y or dy anymore. So that's the way to calculate such a line integral. Then it becomes 3x squared plus 2x dx. And then let's do the integral from a to b, or from 1 to 2. You have this, and then 3x squared plus 2x dx, it equals to d, let's see, x cubic plus x squared. Again, if you're not familiar of transforming this form to this form, or if you're not familiar from here to there, you need to go back to your basic integral knowledge. And then you will do a calculation of x cubic plus x squared from 1 to 2. You just plug in the number 2 and 1 in the equation and subtract from each other, you will get 10. So the strategy here is using just one variable. For example, here you convert, because x equals to y, so you convert y to x, and also substitute dy to dx. Then you get only one variable. You can transform a pass or two-dimensional integral into a one-dimensional integral. Okay, so now let's see. This is for past 2. For past 2, if you integral from a to b, the number is 10. So for past 2, if you integral from b to a, then the answer should be negative 10. If you reversed the direction of the integral, then it becomes negative. So if you want to do an integral from a to c to b, and then go back from b to a, if you do a closed integral, what you will get is 11 subtracted by 10. You will get 1. So that's the solution for this example. Okay, now let's see next topic, which is surface integral. A surface integral is an expression of this form. V, which is, again, in our course, it's a vector function. I suppose again you have learned a surface integral of scalar function, then it will be easier for you to understand the integral of the surface integral of a vector function. But here it's a vector function. It has x, y, z components, um, and its integral of a surface S. dA is infinitesimal area. Here is a picture of a surface integral. For example, if you have a surface here, you want to do a surface integral, for example, in this area. So here, a very small area, it could be defined as dA. And if you can calculate the um, function v here, remember that this function is a vector function. It has three components, vx, vy, and vz. You use the v dot product dA, then you do an integral of the entire surface. You will have the value of the whole surface integral. Where v is a vector function and the integral is over a surface, of course, S. dA is infinitesimal patch of area, which is shown here. And it's a direction. Okay, that's an important problem. So for surface integral, one important thing is the direction of the surface. So the direction of the surface is always perpendicular to the surface. However, we know that um, perpendicular to a surface means there are two directions which are opposite to each other. The two directions perpendicular to any surface, so we can define one of the direction to be positive and the other direction to be negative. So it's always ambiguous. So usually we have to define which direction is positive in examples. And if the surface is closed, then we can use a circle on the integral side. The tradition indicates that outward is positive. So by default, if in some examples it doesn't give you any hint of the positive direction, then let's just see the surface itself. So outward means positive. But for open surface, we have to define a positive surface. Otherwise, it's arbitrary. Okay, so here is a kind of physics meaning of, let's say, surface integral. If the v function, it's a vector function, describes a flow of fluid or mass per unit area per unit time, then the surface integral represents the total mass per unit time passing through the surface, or we call it flux. So this is the meaning or a physics meaning of surface integral. Okay, ordinarily, the value of surface integral depends on the particular surface chosen, but there's some special cases of vector functions for which it's independent from the surface. It's only determined by the boundary line. For example, now you have a boundary line from here to here to here to here. With this boundary line, you may have a lot of different surfaces. For example, the surface, it's difficult to draw because it's three-dimensional. The surface might be something like that, or with the same border line, the surface could be something like that, goes down, or something like um, um, the surface shown in gray. So it has infinity numbers of different surfaces, even with the same boundary. But for some special cases, it only depends on the boundary line. The integral, the surface integral is determined by the boundary line. For such functions, we will have some special class to characterize such kind of functions. Now let's see an example to better understand the surface integral. So let's calculate the surface integral of this function. So again, the function is a vector function. It has x, y, z components. Let's do the integral of this function over 5 sides of a cube. Now we have a cube here. Let's do the 5 side. 1, 2, 3, 4, 5. Now you have 5 sides. Okay, and we choose upward and outward to be the positive direction, as shown in the arrows. Now let's do it. So you can do the surface integral 5 times based on the 5 different surfaces. We will do it together for just one surface, and I'll leave the other 4 as your practice. Now let's see the first surface, which is surface 1. So x equals to 2. Of course, in this surface, the x value is 2. It's a constant. So dx should be 0. But here we don't need dx at all. We just need dy dz, because dA, let's say if we take a small patch of the surface as dA, then dA equals to dy dz times the direction of x, because as shown in the figure, the direction of the surface is the direction of the x. So dA is dy dz. So v dot dA equals to, now let's go back to the function. V is shown here. It's shown here. So now you have dy dz. Let's say, so your dy dz is in x direction, and your dA only has the components of x direction. The dA doesn't have any y direction or z direction components. So when you do the dot product, y and z, in y and z direction, it will be 0. So you only have some equations in x direction. It's 2xz times your dy dz. So it's 2xz dy dz. So, and we know the value of x here. X equals to 2. So it becomes 2 times 2z dy dz. So it's 4z dy dz. And then let's do the integral. It becomes 4 dy and z dz, because dz depends on z. So here again, z dz becomes d 1/2 z squared. So you need to do 1/2 z squared from 0 to 2. It should be 2. And then dy from 0 to 2, it's 2. So 4 times 2 times, so 4 times 2 times 2, you get 16. So this is just one surface, I. You can do similar thing for the second surface, third surface, and the fourth, the fifth. So the answers are shown here, but you can do it by yourself. And then if you want to calculate the total flux or the total surface integral of the 5 surfaces, you just add them all. You will get the result to be 20. Okay, so that's the surface integral. Now let's see the volume integral. A volume integral is an expression of this. So it's a integral by volume. We use V. So T is a scalar function. dt is a infinitesimal volume element. In our Cartesian coordinates, of course, dt equals to dx times dy times dz. For example, if T is a density of substance, which might vary from point to point, because not all the material has a uniform distribution of the density. For some substance, the density might be different. It might be a function of x, y, z. So if T is a density of a substance, then the volume integral would give the total mass. Occasionally, we shall encounter volume integral of vector functions. So if it's a vector function, then v dt becomes vx plus vy plus vz dt, and then it becomes vx dt in x direction, vy dt integral in y direction, vz dt integral in z direction. Because the unit vector x, y, z are constant, they can come outside the integral. So here we write it outside the integral. Now let's see one example for volume integral, which is a scalar function of t. So here you see t, it's x, y, z squared. It doesn't have any x component, y component, z component. It's just a scalar. So we want to do the integral in this figure. So it's pretty straightforward. You just write the equation here, t dt integral. The function t is x, y, z squared. Dt is dx, dy, dz. So for x, you write it here, x times dx, then you can combine x into dx. And then you write y here times dy, and z squared here times dz. So you need to first do the integral inside the squared bracket, and then do the integral in the curly bracket, then do the integral outside. One thing you need to be careful is when you do x dx, the boundary of x dx is from 0 to 1 subtracted by y because of this line. It's 1 subtracted by y for x boundary. And then for y, it's from 0 to 1. For z, it's from 0 to 3. And then you just do it step by step. Then you can get the final answer, which is shown here. Okay, so that's all for all the integrals, including line integral, surface integral, volume integrals. Before this lecture, we suppose you have already be very familiar with the basic integrals, including basic scalar, basic line integrals for scalar functions, and you're also familiar with surface integrals for basic scalar functions. If you're not, please go to these 2 videos to get yourself ready for this whole lecture. So that's the entire lecture for the integral. So I will stop here, and I will see you next time.